We saw that truth tables are useful for many things. We can use them to show that a sentence is a tautology, a contradiction, or truth table contingent, and we can also use them to show that multiple sentences are jointly satisfiable or tautologically equivalent, and we can use them to show that given premises entail a certain conclusion. Now, when it comes to constructing truth tables for multiple sentences, the task can quickly become very cumbersome. So think about truth tables for 5, 6, or 7 sentences. They can be gigantic and a lot of work to put up. So it is often useful to think about ways of making our work easier and answering certain questions using partial instead of complete truth tables. For example, we can in fact show that a given sentence is not a tautology by means of just one line of a truth table. Why is that? Well, a sentence is a tautology if and only if it is true on every possible valuation. So that means that a sentence is not a tautology if and only if it is false on just one or more valuations. So showing that a sentence is not a tautology merely requires showing that there's one line in its truth table in which it comes out false. Similarly, showing that a sentence is not a contradiction merely requires one line in a truth table. Why is that? Well, a sentence is a contradiction if and only if it is false on every possible valuation. So showing that a sentence is not a contradiction merely requires us to find one line in its truth table in which it comes out true. So to show that a sentence is not a contradiction, you merely have to construct one line in a truth table in which it is evaluated as true. Okay, let's look at an example to see how we can use truth tables to establish that a sentence is not a tautology and not a contradiction. This sentence here is neither a tautology nor a contradiction. What we have is a conditional, and the antecedent of the conditional is a conjunction, and the consequent of the conditional is simply the letter S. Now, we see in the second row of this truth table that on a valuation where U and T are true, and so the antecedent of the conditional is true, but S is false, the whole conditional is false. And so that means that this sentence is not a tautology, since there is a valuation on which this sentence is false. But this sentence also is not a contradiction. And the reason is because there are valuations on which this sentence is in fact true. So to illustrate, just look at any other valuation other than the one represented in the second row. So for example, if we look just at the first row, when U, T, and S all are true, that means that the antecedent of the conditional is true and the consequent is true as well. And so the whole conditional is true. And so given that there is at least one valuation, in fact more than one, on which the conditional is true, that means that this sentence is not a contradiction. Now let's sum up the cases in which you can get away with a partial truth table. If you want to show that a sentence is a tautology, you need a complete truth table. But if you want to show that a sentence is not a tautology, you merely need a one-line partial truth table. Similarly, in order to show that a sentence is a contradiction, you need to construct a complete truth table. But in order to show that a sentence is not a contradiction, you merely need a one-line partial truth table. Showing that two sentences are tautologically equivalent requires a complete truth table, but showing that two sentences are not tautologically equivalent merely requires one line in a partial truth table. Specifically, you only need one line in a truth table in which the two sentences are evaluated differently, and one of them is true and the other one is false. Showing that two sentences are jointly satisfiable requires just one line in a truth table in which they have the same truth value. But showing that two sentences are not jointly satisfiable requires a complete truth table. You need to show that they have different truth values on every possible valuation. Now, in order to show that given premises entail a certain conclusion, you need a complete truth table, and you need to show that every valuation that makes all of the premises true also makes the conclusion true. Now, in order to show that given premises do not entail a certain conclusion, you merely need a one-line partial truth table. Specifically, you only need one line in which all of the premises are evaluated as true, but the conclusion is evaluated as false. Now, we saw that every tautologically valid argument is also valid, and so to show that an argument is valid, you can construct a complete truth table which establishes that it is tautologically valid and therefore valid. Now, in order to show that an argument is not valid, you need to supply a one-line partial truth table in which all the premises are evaluated as true, but the conclusion is evaluated as false. And furthermore, you need to supplement this truth table with a quick argument showing that this one line in the truth table represents a genuinely possible scenario. Now, there is an important caveat to what I just said. I said that there are all these different cases in which you need a complete truth table, but if you think about it carefully, you will realize that often you can in fact avoid constructing a complete truth table simply by supplementing a partial truth table with an argument. For example, we said that showing that given premises entail a conclusion requires a complete truth table. But you can in fact show that given premises entail a conclusion by means of a partial truth table, as long as you supplement this truth table with an argument. So for example, consider this argument. It has three premises and a conclusion. The three premises are not A or B and C, or B or C. Sorry, not A or B or C. That's the first premise. The second premise is not C or D. And the third premise is it's not the case that B and not E. And the conclusion of the argument is D or not A or E. Now, this argument has 5 atomic sentences. Constructing a complete truth table for this argument would require 32 lines. That's big. Can we avoid that? The answer is yes. We can avoid constructing a complete truth table and merely provide a partial truth table as long as we supplement this partial truth table with an argument. Let's see how we can use a partial truth table in order to establish that an argument is in fact valid. So here's our argument. We have 3 premises. The first premise is that not A or B or C. The second premise is not C or D. The third premise is it's not the case that B and not E. And our conclusion is D or not A or E. And I'll just put an exclamation mark above the conclusion here to remind you that this is our conclusion. Okay, so this argument is valid if and only if every valuation that makes all the 3 premises true also makes the conclusion true. So let's, for the sake of argument, suppose that this argument is invalid. So if this argument is not tautologically valid, that means that there must be a valuation that makes the 3 premises true and that makes the conclusion false. So let's suppose there is such a valuation. So if there is such a valuation, that means that this valuation would render our big disjunction in the end here false. Now a disjunction is false if and only if both disjuncts are false. So that means that D must be false, and our second disjunction here, not A or E, must also be false. Now if not A or E are false, that means that not A must be false, which means that A must be true and E must be false. So simply by supposing that our conclusion is false, we have already figured out that A, E, and D must have very specific truth values. So A must be true, D must be false, and E must be false. Let's just enter, let's look at the second premise now, not C or D. Now if D is false, then our premise is true only if not C is true. And not C is true only if C is false. So if there's a valuation that makes the conclusion false and all premises true, that valuation must assign the truth value F to the sentence C, since that's the only way of making our second premise, not C or D, true. Let's next look at our third premise. So our third premise says that it's not the case that B and not E. Now if E is false, that means that not E is true. And if we want this whole negated sentence to be true, that means that the conjunction must be false. And now since the second conjunct is, given our assumptions, is true, that means that B must be false. So what I've just argued is that our third premise is true if and only if B is false. Given that our second conjunct, not E, is already true, given that we have said earlier, and given that we want the whole conjunction to be false. Okay, so a valuation that makes all of our three premises true must assign the truth value F to the sentence B. But when we now look at our first premise here, we notice that not A is false, given that A is true. And we also notice that B or C is false, given that both B and C is false. And so that means that our first premise must be false, since it is a disjunction and both disjuncts are false. So what we have seen is that if we suppose that our conclusion is false, there's no way of assigning truth values to our 5 sentences that makes all of the premises true. And that means that every valuation that makes all of the 3 premises true is also a valuation that makes the conclusion true. And that means that this argument is in fact tautologically valid. Let's sum up the argument. We saw that the argument from our 3 premises to the conclusion that D or not A or E is valid because there's no valuation that makes the premises true and the conclusion false. To establish why that is, consider the following partial truth table. If the conclusion is false, then not A must be false, which means that A must be true, and D must be false, and E must be false. But if A is true and D and E are false, then there's no way of assigning truth values to B and C that makes the 3 premises true. In particular, if D is false, then the second premise, not C or D, is true only if not C is true, which requires C to be false. And if E is false, then the third premise, not B and not E, is true only if B is false. But if A is true and B and C are false, then the first premise is in fact false. And this shows that there's no way of assigning truth values to the 5 sentences A, B, C, D, and E, which makes the conclusion of our argument false and the 3 premises true. And that means that this argument is tautologically valid.